It's okay, so closely following DHT, the next presentation is DHT2. It's kind of made some things easy for me because, you know, Du's already talked about DHT. So before we start, I'm Shyam Ranganathan. Shyam for those of you who know me, Shyam for those of you who don't know me on IRC and other places. I work at Red Hat, I'm a developer, that's about it. I've been working on DHT, some parts of GFAPI in the past, and been dabbling around with various parts of Gluster. And because I worked on DHT is why we're talking about DHT2 and at least, some ideas and things about how we can improve DHT. So the title of the session is loosely inspired from the movie Oh Brother Where Art Thou? And the only movie reference is in this slide, which is the agenda, so you can forget about the movie. And you don't even need to read the stuff in quotes if you're not interested. So what are we going to talk about? We're going to talk about why are we doing DHT2, what is DHT2 in terms of its design, and what are we trying to do? How does DHT2 work? Then we'll talk about challenges in DHT2, and we'll talk about challenges because of DHT2, and finally touch upon where exactly are we, what the heck's happening here. So with that, let me get in. So why are we doing DHT2? Du's talked about a bunch of problems in DHT. So that's covered, but let's just distill some of these problems. So we have directories everywhere. We've heard a series of problems because of that. We have the layout per directory. We've heard a series of problems because of that. We've talked about rebalance a little bit, but one of the points we didn't touch upon was rebalance is kind of heavy today because the amount of data that moves around is larger than necessary. So it's not optimal. You can probably never come down to perfect rebalance, but there are optimizations here that can be done with the amount of data that's being moved. And of course, all this impacts scale and correctness. Again, I'm just going to refer to the previous presentation for the problems, because Du's done a good job. But I just wanted to point out a couple of things from that presentation when Du said, what are the advantages of DHT? So one of the things is DHT is pretty good for small footprint servers, small footprint clusters where the number of subvolumes don't change. Pretty much things like virtualization workloads where you're dropping in a few VMs and life's good. It's pretty good for worm workloads, write once, read many, because your file location A doesn't change, B doesn't grow, you don't face min-free disk problems, so on and so forth. So there are use cases where DHT is actually pretty strong. You don't need to think about other alternatives there. Just wanted to make that point because I didn't want it to sound like DHT is like, what the heck are we doing with it? No. So anyway, we've touched upon this. So I also just added that we can address correctness in DHT. We probably cannot address scale. We can address correctness. Du's gone through again a few options there. So we can do broader locking semantics for directories and layouts and ensure the correctness of stale layouts, so on and so forth. But basically, this increases the complexity of the code. It just makes it more and more difficult for people to continue developing on that piece of software. Okay, so with that, we move to DHT2, which will solve all these problems for you, and it'll be the best. So let's get into DHT2 now. So what is DHT2? It's basically we're looking at the file system as a collection of related objects. So if you're going, hey, that's what a local file system does. It is a collection of related inodes and data, right? So yes, it's exactly that, but it's not distributed in the sense. A local file system is obviously not distributed. How do we take these objects and we distribute them? That's the challenge that DHT2 starts addressing. So if you look at the file system objects, what do we have? We have directory inodes, we have file inodes, and then we have data pointers. So you have directory objects, file objects, and data objects. Directory objects pretty much maintains the hierarchical information. It says who are my children and what are their inode numbers or GFIDs. File basically maintains the file inode basically maintains the metadata about the file, and it has data pointers that has the real data about the file. So with that, so let's consider a simplistic view of a very small example here. A client view could look something like this. You have the root of the volume, and you have dir1 and file1 as children of root, and dir2 and file2 as children of dir1. So this is a very simple client-side view of this particular listing. So what are the objects? There are two classes of objects here. There are inode objects and there are data objects. So we group them into inode and data objects. So the inode objects are again of two types, file and directory, that I already said. So we put them there, and we have file data, which is another class of objects. We put it on the other side. And so I just denoted file objects with that yellowish color and purple for the directory objects, and we've just named them. And so to really get the client view, what do we do? Root points to file1, root points to dir1, dir1 points to dir2, and dir1 points to file2. And the association of the file to its data is basically the file points to its respective data blocks. All simple local file system 101. Alright, so now let's talk about how we're going to distribute this. So this is what it is, the objects. What do we do with its distribution? So what we do is, instead of inode numbers, we're going to use GFID from now on, so that it's Gluster specific. And so we distribute inodes using its GFID. And because we classified the objects into two sets, we're going to put inodes, all inodes, into the metadata ring or the inode ring or whatever you call it. And also a directory is just going to be present on one subvolume of that metadata ring. So it's not going to be present everywhere. It's an object, it has to live in a place, it doesn't have to live everywhere. For the data side of things, we'll use the same GFID of the file and put its data object on the data ring. So if you kind of look at this, from a namespace perspective, we need two rings because a file's inode will have the same GFID and a file's data will have the same GFID. So you cannot kind of have a namespace collusion if you're just going to go into .glusterfs and create two such objects. So you need the namespace segregation and also possibly need the ring segregation so that you can handle other characteristics of data and metadata separately. So what this brings about is the distribution is no longer name dependent. It is GFID dependent, or you kind of, in DHT we used to hash the name and figure out in the layout where it goes, whereas here we just have the GFID and that's going to tell us where it lives. And the other thing is, we really do not need multiple layouts here. In the name-based scheme of affairs, one of the intentions was similarly named files shouldn't rest on the same subvolume. All README shouldn't go to the same subvolume. I sometimes feel that's a weak argument, but that's just me. But anyway, so in this particular case, we don't do it by name, and we just have this one big layout. Of course, we can have a different layout for the metadata ring and a different layout for the data ring. And we hash by GFID. So there's only one single layout that we use to distribute the data. So if you're starting to see similarities of problems presented in DHT2 and the kind of solutions here, it does flow from that, in case you were wondering. Okay, so let's go back to our example and complicate it a little. So let's get rid of the names, because we're no longer dealing with names, we're dealing with objects, and these objects are named by their GFIDs. So I've chosen a random set of GFIDs there, except for root, which is a well-known GFID of all zeros 1. So that's your root object. It of course has the entry table there, or not the entry table, it will be the name inode table within the directory object, which says who are its children. And then you have VA11, which is dir1, and 00EF, which is file 1 now. That association can be seen there, and so on and so forth. We have BAC5 general object numbers, but the relationship is really maintained by the directory objects. You still have your data objects here. So if you start drawing the arrows again, we just end up with the same diagram because the relationships are maintained. So you just get back to where you started. Any questions here? Just checking. All right, so let's continue more on distribution. Okay, so what we just saw is we're using the GFID and all that. That's fine. But what else are we doing with distribution? So the first thing is, what's the layout based off? The layout is based on a concept of buckets, where you have far more buckets than you have subvolumes. So that you can distribute these buckets to subvolumes. And we do a further thing. We actually encode the bucket ID into the GFID. So let's say we take off the first 2 bytes of the GFID and encode the bucket ID into that. Or take out the first byte. It really depends on how many buckets you want. So if you just take a byte, you get 255 buckets. If you take 2 bytes, you get about 64K buckets. One may make sense for the metadata ring, one may make sense for the data ring. But basically, if you just ensure we have far more buckets than subvolumes, we have a larger distribution of the buckets across the subvolumes. That's the intention. The second thing, what it does with these, so anyway, so once you have that, given a GFID, you'll be able to extract the bucket ID because it's encoded in the GFID. And GFID based lookups are trivial. So you just send your op or lookup, whatever it is, down that bucket and you find the object there. It doesn't have to be redirected. There's no link to, I mean, it has to be there. So if it's not there, there's a bug. So that's A. And the second thing we do is, if we just did the bucket ID and spread all inodes everywhere, we're going to have some trouble doing read diffs. We're going to have an accrued cost of lookups because we're going to have to do a 2-hop when we do a parent GFID base name based lookup, because we'll go to the parent GFID subvolume and then look for the name and its GFID and then go hop to another bucket. So what we additionally do is we co-locate the file inodes under the parent directory. And how we do it is simply using the same bucket number as the parent during the creation of the file, which is what I'm talking about as statically inherits the bucket ID of the parent. So, or at point of creation, it inherits the bucket ID of the parent. So what this does is file inodes and its parent will share the same bucket, and hence they'll be co-located, and your read dir p operations, lookup operations do not hop subvolumes. They just go to a single subvolume. Of course, this will break when you do non-trivial renames. And what is a non-trivial rename? Basically, if you rename a file out of one directory to a completely different directory, because then your two directories may have different bucket numbers, but the file will still retain the initial bucket number that it inherited from its original parent. So when you have non-trivial renames, yeah, you're going to lose this, but that's fine, is what I'm saying. But if you're going to rename within the same directory, change the name of the file, create a temp file, rename it within the same directory, the bucket number is going to be retained, and it's just going to be co-located with the parent anyway. The other thing, of course, where this co-location will fail is if you have hard links. So if you create a hard link, the name is going to be on a different, under a different parent directory. If the hard link is under a different parent directory than what it's pointing to, then then there will be a redirection because the object is unique, and so it won't be co-located. But with co-location, basically we get optimized PGFID base name based operations, so that it just has to go to one subvolume. So let's go back to our diagram. So what we do initially here is let's add some servers. So all the newer, smaller black dots are subvolumes or bricks to DHT2. And so we just added 2 in the metadata, 4 in the data, just because we say we can have fewer metadata servers. And now let's assign bucket IDs to them. That's what the layout does. I mean, layout says, okay, let's give bucket 0, 0 to that particular node, BA75 to this particular node on the metadata ring, and just assign 0, 0 and BA to some random nodes here. So here the bucket is the first byte, and I'm only showing 3 buckets because most of my GFIDs fall under those 3 buckets, so I don't have to kind of show all 255 buckets. But the idea is assign buckets to subvolumes. And once you've done this, it's kind of pretty easy to see that the root object would go sit in that particular subvolume, because its first 2 bytes are 0, 0. The first 2 bytes is where we have encoded the bucket ID into the GFID. And B and C kind of go to the other subvolume because bucket BA and bucket 75 belong to that subvolume. And initially I said the GFIDs are chosen at random. They're not, because I wanted to show co-location. So the file GFIDs are actually chosen based on the same, they have the same bucket ID as their parent. So file 1, which is under div 1, actually has 0, 0 as the bucket ID. So, yes?
One question. So these buckets, are they just a mapping from the GFIDs to the bricks? Or is that more? Is that even let's say, a subdivision of the brick space?
Okay. So the question is, are the buckets mapped from the GFIDs to the bricks, or is there something more? Right? I'll answer it this way. So in this example, I've only shown 3 buckets based on the GFIDs in the example. Whereas I should call this out as this is a 1 byte bucket. So there are actually 255 buckets. Considering the same example on the metadata ring, we have 2 subvolumes. So they'll be evenly divided between the 2 subvolumes, 256, 0 to 255. So it'll be 128 per subvolume, 128 buckets per subvolume. So that's the layout. The layout does not derive from the GFID. The layout derives from what's your max buckets that you're going to support, and hence distribute those buckets across the subvolumes. GFIDs are randomly assigned to directories, but the children, the filed inodes inside that particular directory are assigned buckets based on the parent's GFID. Did that answer your question? Sort of. Okay. Okay. So the files co-reside, the file inodes co-reside with the parent inode, and well, the data pointers, they just go to whichever buckets they belong to. It that doesn't really matter. So let's talk about a rebalance with this whole picture in mind. Okay, I mean all this is fine. Okay, another question.
We had this case sometime ago where the customer was creating, every day they were creating a directory and creating hundred files. So does that mean all your load is going to be once a month?
Okay, so the question is, there is a case where a daily directory is created and all data pumped into that daily directory, and in which case what happens? Does all the load go to a particular subvolume? I have a clarification question here, is that there are no subdirectories under that daily directory. Is that what you're saying? Okay, so let's just say yes. So actually there are two parts to this answer. If there are subdirectories, well, then they can go into other subvolumes. But if it's one large directory, one directory with a large number of entries in it, then we've not yet handled that problem. Okay, so we are aware of this problem. As a matter of fact, in Barcelona, when DHT2 was first presented, I think one of the questions was what DHT provides you with this distribution of entries across how many ever subvolumes you have, because the directory is everywhere. Whereas DHT2, everything goes to the parent. Aren't we talking about too many entries under the same directory? So I don't want to get, we have some answers yet. We are thinking about the problem and kind of seeing how to shard directories in DHT2 better. Do we get that day 0? I don't think. Day 0, day 1, I don't think so. But not having that could potentially be a problem in certain scenarios like you explained. So we will probably look at it. Yes?
That's a clarifying question. It's only the metadata that's stored along, right? It's not validated, so you have to have a very large number of file metadata for it to make the actual subvolume respond, right? The actual data would be spread more widely.
Yes. So to repeat the question, because it's only metadata on the metadata ring, isn't this not a problem till we reach really high scale? Yes, that's a large number of entries. Yes, that's true. So the data would be spread different. That's true. So the data would be spread differently than the metadata. I mean, we are going to have two layouts. It is going to be based on the GFID. The distribution is going to be based on the GFID, but the layout's not going to be buckets. That would be dumb, because everything would just go to the problem of large directories would just exaggerate itself. So no, the data would be distributed separately. So yes, but here's the thing. Okay, so I'll voice my concern on this in the sense, I agree, and that's why we're saying day 1 we're not going to have this built in. We'll probably think about it later. But distributed file systems with single MDS, we don't have a single MDS. Okay, so take that out of your head. There's a ring. So distributed file systems with single MDS, like I don't want to give examples, but let's say other distributed file systems. So the Achilles heel is always been quoted as having a single MDS because of metadata operations, because of all the locking going into that particular metadata server and all that. Is it because of a single directory having a large number of entries? I'm not sure of the use case, but having talked to a few people who wrote those distributed file systems, it looks like something that we need to handle. So we can talk about it more, about ideas, how we borrow stuff from XFS and stuff like that, but it's under consideration, not a part of the slides. Okay, so let's talk about rebalance, right? So one of the things is fixed layout is instantaneous. There's no more mucking around with all directories and changing stuff in all directories and all that. So fixed layout's like bang, done. That's because we just need to reassign buckets to the added subvolumes or steal buckets from the removed subvolumes and then map it onto the other subvolumes. In other words, there's a single layout. I mean, how much time is it going to take to change a single layout? Right. It's not going to take much time. But having fixed the layout is not enough, because just because you fix the layout doesn't mean that all the objects have moved, right? That is going to take time. Rebalance will take time. fixing the layout will not take time. The other thing with reassigning these buckets is collocation property is retained, because the parent and the child share the same bucket ID. So even after a rebalance, they'll still continue living in the same bucket. So the collocation property will be held across cluster expansion. That's just FYI. There are some cases in rebalance in DHT that I believe worm workloads use, which is to add capacity but not do a rebalance because rebalance is costly. I'm probably looking at Richard here, but I think that's what happens. Where min-free disk is actually used, and because it's a worm workload, you really do not accrue more space on the older subvolumes, and newer directories are just going to spread themselves on the newer bricks, so on and so forth. This is a slight bit of a challenge because we really do not want to hold on to any information on the directory inodes and get into a case of a series of problems like DHT. But we are considering things like layout versions and layout history, so that you came from a layout to another layout, so you maintain the history, and you mark directories based on which layout history version they came from, and so you know which space to look at. But the idea on the metadata ring, or the intention on the metadata ring, would be to arrive at clear balance rather than leave it in this state of histories. The data ring may be left in the state of histories primarily because it takes more time to move data. The other part of DHT for this comes under rebalance, where we are splitting the client and the server, is but it has a correctness angle to it, and it has the rebalance angle to it as well. So we want to split this into a client and server model, where a client simply looks at the layout and redirects operations to appropriate subvolumes. The server takes care of coordination of the operation between an ongoing rebalance and or ongoing other I/O, or using transactions for maintaining the consistency of the operation. The transaction part is very simple. In DHT2, if you look at it, you'll create a GFID and then you link the name into the tree, into the parent inode. So if you create the GFID and then you crash, what happens? Or you actually have an orphan GFID, you're going to leak space. So you basically need a transaction of sorts there to say that you've done something and you've not completed the operation, hence there's some cleanup left. So that's the transaction part. It's pretty much only for orphan GFIDs, not found a case where it's for anything else. So that's why there's a client and server split. So we did the POC, and from the POC we kind of realized that if we do some of the operations, like if the client really goes and creates the GFID and then goes to another subvolume and creates the name, who maintains this transaction? We don't want to leave it to the client. I mean, we really want to take control of the transaction. We cannot just leave it to the client. Client goes away, what happens? It's just ugly. And if it never comes back, what happens? But then the subvolumes, the servers, the bricks, that's what we control, and so we want to kind of shift this model this way. It can be seen as an issue, because what we are really saying is, once we do this, where does AFR and EC lie in the stack? Below DHT, above DHT? And if you're actually going to move this to the server, then that means all those guys move to the server. But at least in the metadata ring, this would be a need. I already touched upon two rings having different layouts and layout strategies and stuff. So that's some ideas about rebalance and what we intend to do there. Okay, so some further challenges in DHT2 based on all this, on all of the design. So rename is going to be very interesting, because rename needs to do e-loop checking. To do e-loop checking, you need hierarchy, because you need to kind of go back and say, am I forming a loop or not? And directories are not co-located, so basically they're going to just split across. You're going to have to hop subvolumes to do this. But it's not all that gloomy. So basically, a local file system also takes the it locks the file system up when there's a cross directory rename, just so that there aren't two cross directory renames in progress, and hence a loop creation because of the consistency of the operation. So we would do something similar, but what that does is that it makes, if you're doing non-trivial directory renames, you're going to get into e-loop checking. Okay, if that's your use case, I don't have any great ideas yet. So that's where it is. Of course, this will need object back pointers. Arvinda actually has a thread going on that in the lists on PGFID base name on the data on the file object so that you can kind of go back. We'll also probably need that for some sort of an FSCK on this because let's face it, the file system no longer looks like a regular file system anymore. It's just a bunch of objects, so probably need a few things there. The next one, which again do touched upon a slide, in DHT the data and the metadata co-reside, whereas in DHT2 the metadata and data do not co-reside. There have to be means of synchronizing the size and time information across operations on the data side to the metadata side. The current thought around this is pretty simple, is that we'll maintain dirty inodes on the metadata, and so any stat on the dirty inode will actually visit the data, get the latest information and pop it back. And on last FD close, it's no longer dirty, it will kind of take the last fresh copy from the data side and move on. But what this throws a wrench in is anon FDs in Gluster. So anon FDs are like, boom, these FDs that people can just use anywhere. And after looking at DHT2, I've started hating it, but you know, that's life. So we need to see how to handle anon FDs, because if either handle anon FDs or just get rid of anon FDs, one of the two. Anon FDs do have their uses in NFS v3 a lot, because NFS v3 does not have an open, but Ganesha does do this open and retains that open FD and does further operations on that. So that model seems attractive. We encourage everybody to do that. So that's another one. The orphan GFID cleanup stuff, I talked about transactions in a couple of slides earlier, so not talking about that. Yeah.
So one more thing about this data metadata co-location, right? So at the moment, there is I mean, almost everybody kind of tells that Gluster is very slow for small files. Now with DHT2, if we store metadata and data in different places, things like CP minus R and all these things will probably become even more slow, because at least in with co-location we have this GF content key that we create for users to get all the data in lookup itself.
So I've touched upon the quick read. That's what it is, right? I touched upon quick read in the next slide. I know we had this discussion on Devil on quick read. We discussed some solutions. I'll just get to that question a little later and repeat the question too. Oh, directories as a DB. Oh, this is going to be fun. So basically, after having said all this, there have been conversations around representing the directory as a file. We are thinking of just moving the whole MDS back into a DB, but the intention is the same with respect to keeping the directory as a file. Helps us control DOF, so you don't have DOF related, reminder related problems. Further, what happens with DHT2 is we'll just eat up two inodes on a server, on a node in the local file system if you don't do this, because you'll have the name object and then you'll have the actual GFID object on the local file system, which is two inodes. But you don't need that. And so that's something that we are looking at. Again, that's not day 0, day 1 activity, but once we prove that this actually works and it'll do stuff, then we kind of get into that. Okay, so challenges because of DHT2. Okay, so here's where Pranit's question was, what happens, in short, what happens to quick read in CP-R workloads where the GF content key comes back? I mean, which is bullet number 2 here. But so we did discuss in the Devil lists about this, and the idea was to cache, to have small file content in the MDS. I would say I'm not in favor of that. I would rather do asynchronous, post lookup asynchronous fetch of the data and measure what happens. I'm not saying that's what we'll do, measure what happens, and then take a call on, what do we need to do with the GF content key at present. I just don't see data sitting in the MDS, and that doesn't seem to fly to me. So that's addressing that particular concern. One of the other things is IO path cannot really depend on hierarchy, cannot do hierarchy related operations. Best example is quota. To go update the quota on all parents, it's just not possible in the IO path because there is no hierarchy in this particular system. The hierarchy is, well, explicit, implicit, what? It's not on the backend system. So that's that. Anon FD based operations we covered. There are some other things here. What happens to change log? Do we really need EC on the MDS? I mean, EC is for data, so do we really need EC on the MDS? So maybe we just not have EC as a part of the MDS stack. What happens to tiering? I mean, tiering has been DHT over DHT. Of course, it can continue that way, but are there advantages, disadvantages that with this model that tiering can leverage? And for example, one of the cases is sharding may unfortunately accrue a cost based on this particular design because it has to visit different inodes, and the data in inode is not co-located, and the shards hence are not co-located. So there is that cost that could accrue here. And of course, the last bullet saying unknowns. So as you think and sync this design and what other things crop up in your mind, what may work, what may not work, we definitely want to hear so that obviously we can try and see how to address it or improve the situation. Okay, where are we with respect to DHT2? Quick slide. So introduced in Barcelona, thanks Jeff. And Jeff followed it up with 2 documents discussing the overall architecture of DHT2. References are provided there. Quite a few of you participated on that. Touches upon a lot of the topics that we've talked about today. Then we did the POC, that's like Venki, Kotresh, and me. Learned a few things from the POC. POC was done off tree. We'll not go into the reasons, but it was done off tree. And then right now we've moved back to master, and we've done this shell translator there. So if you're going and looking at it and saying, what the heck is this? Yeah, there's nothing more. It's in a limbo since then, but it's not out of the picture yet because we do see the contrast of DHT. We do see the problems in DHT. So is DHT2 the answer? We still need to find out. So till we find that out, it's not yet out of the picture is what I would say. And so the intention is to get an experimental release on 4.0 so that people can at least test it, get a feel for it, and see how it works, give us feedback, things like that. And I don't know whether we have a session on Gluster releases. So 4.0 is about 9 months away. Amy agrees, so that's it.
Sure. You're one of the ones who get to build it.
That brings me to the end of this presentation. And this is again a reference from the movie. I'm sorry I said I won't do it, but yes, question.
You're describing how the parent and child are always co-located, but isn't there kind of like a hierarchy? Because you have like the root, and then the subdirectory, and then the sub-subdirectory. How do you determine, how is everything not just co-located with G root, right? With the root 0?
Okay, so the question is, you talked about parent and child co-location, and so then how's not parent and the child is a subdirectory co-located, and hence everything just falls into the same subvolume, right? So actually, if you go back to the example, a directory child will get a different bucket ID than the parent, and so it will spread differently.
How does that help you optimize? Like when you were saying like when you want to list the directory, it's really fast because the child magnets are co-located. But obviously you want to know the subdirectories too. How do you know where to go look for those?
Right. So the question is, how does this optimize read dir for directories when there are directories as children of a particular directory? So that's a fair question. It does not. The co-location was primarily when initially considering this and spreading all inodes across all buckets. That would really suck because then read dir and file ops will be slow. We'll take a 2-hop instead of a single hop. It will have to go to find the GFID and then go to another bucket to do something else. So it's actually an optimization in the DHT2 design to kind of at least co-locate the file inodes and the directory and the parent directory inode. Subdirectories are not co-located. Having said that, we will be borrowing, and having represented a directory content as a name, GFID, we would actually do something like represent it as name, GFID, D type, the stat type of the file. Simply borrowing the idea from ext4 and XFS actually, just so that on a read dir you can at least get the type. Read dir p, you can at least get the type. On a read dir p, that's enough. On a read dir p also, that is possibly enough, at least in NFS workloads. NFS workloads does not say just because I did a read dir p I have to return the stat data of the file. I could not choose not to, and NFS would do an explicit stat. One alternative. Another universe, Fuse. We'll have to kind of go through the directory entries and start them and then send the data across. Go to a different subvolume and do it. So that part's not optimized. That's it.
Even in Fuse you can set the inode null and it will do it.
Yeah. So the cost is 2 ways. Okay. So the thing is, it'll do an explicit lookup. Okay, so the thing is, there is going to be an explicit lookup that's going to come your way if this is a directory object, which is going to cost the application. Whereas in the previous case, a reader if it returned everything that it wanted, is probably not a lookup. But I'm not saying I'm lying, but I'm not saying the right thing there, because in our Fuse implementation right now, if you do the FOP, the lookup will happen.
Yeah.
Right. But that we'll wait for Purnima's presentation to see how we can optimize that, I guess. So preventing of that lookup, right? I mean, not only that, but other parts of it. But yeah, that's what's going to happen. So we'll return D type.
I think the part that I get when you read the directory, you don't know whether it's lots of content typing. I don't know if it's just files, mix the directory to files. I think the part that I'm not quite following is how do you not have to go look at every sub-volume to exhaustively determine what the contents are? Like, did the directory deterministically go somewhere else for that merit?
So how do you determine the, I'll change the question to, how do you determine the type of objects under a directory? Just visiting the directory inode and its contents.
Sure.
So it not only stores name and inode, it stores name, inode, and D type, which is what, if I'm not wrong, like ext4 and XFS do that, just so that they can return the. So it's the same problem that XFS faced, and interestingly there was a thread about it, where it had to visit the inode just to return the D type, inode of the file, or the directory, subdirectory, to return the type of the object. Whereas the optimization.
I think this is a different question. I think you're asking how to find where the subdirectory lives, right? When you're reversing through the top directory. I think maybe, are you saying that when you basically look at the directory, you could know deterministically, this directory contains only files, and thus I don't have to look at the subline that I get full file metadata for this directory and is full of it.
Let me do one thing. Let's take that question offline,
Okay.
so that we can draw it up and kind of see where we go with it. Any other?
But you're right. I mean, D-type is new in XFS. Users notice that's there. It's been around pretty for a while, and it doesn't help. So you could, in that case, where you're recursing your case, you're iterating your direct matrix, you don't have to put this down or figure out, no, this is a directory or file. So you have all files as subdirectories, you'll know your locality of your metadata.
Yeah, that's why I was pulling in the D type into it. But we'll draw it out.
Yeah, two quick questions. So this is the distribution is very similar to how Swift does it with partitions and all. So one problem they faced there was the number of buckets you can have. So is that fixed, or can that be changed as the cluster grows? And the second one is as soon as you do a write call, the end time changes. So how does that fit in?
So yes, the question is, Swift does something very similar in terms of partitions. And so what if you increase the partition count, or what if you increase the bucket count in this particular case? And let's take that question first. Bucket. So I've had this conversation on this particular topic actually with a few of you here, including you. So the intention there is we have fixed number of buckets, and we keep the buckets large enough that you don't get. I mean, we are looking at 64K buckets. I mean, if you're going to have 64K servers, somebody else's problem, not mine, because probably I'm dead. So that's answer A. The second part of the question was when you do a write, end time changes in the data object, how does it sync back to the metadata? So that's where I touched upon the dirty inodes. So what happens is, so here's the thing, you cannot just go do a write. You have to open an FD and then do a write. Hence, anon-FD mess. But when you open an FD, you have to open an FD. Where do you open the FD? You open the FD on the data, or do you open the FD on the metadata? So I say you open the FD on the metadata. So once you open the FD, the metadata server knows that this inode is open for operations. So it's dirty. A stat on that object will not return results from the local cache or local on-disk data. It fetches the data from the data servers or data vault subvolume and then return the stat metadata.
If that's that.
If it is stat. The server. So basically, for me, I know how many FDs are open on an inode, and I know the inode is dirty. I'm not saying FD is dirty. So that's the idea. So all open files will go through a 2-hop on a stack. Yes. Yeah. But once you close, I don't see that as a problem. I mean, I have been pointed to instances of virtual images and they have single large files and maybe they do a stat every so often. Are you going to do this redirection every so often? But I don't have statistics around that to kind of say that's bad. But yeah, once we get that, probably we'll know better. But that's what will happen.
Other questions? Tons. All right. We'll keep going.
I'm going to let you interrupt.
Yeah, no, it's fine. I'll let you know where the schedule has changed. I've already changed in my head, and then I'll let you all know.
Okay.
Go ahead.
Dipin. Yeah.
So I was worried about how we will be listing subdirectory. We can take it later on, but the files inside the directory. So suppose we have renamed some file and the bucket ID has changed, but it is still located in the old bucket, right? So when we are listing a bucket or a directory, how do we list those files?
So how will we list files that have been renamed and hence now are under a different parent on a different bucket? The bucket ID for the file will not change. The inode number of the file will not change. Okay. So simply put, what will happen is listing or lookup or whatever operation will basically return an e-remote because it will check the PGF ID. So it's a PGF ID comma base name operation, let's say. Okay, it's a lookup. So look at the PGF ID, it will find the base name, it will find the GF ID of the object because that's there in the directory inode table. And then it will get the bucket ID from that GF ID. If that bucket ID does not belong to the local subvolume, it has to do a remote operation. Now there are two ways to do this. The server does it for you or just passes it back to the client and asks the client to do it. Right now we are dabbling with the client doing it or the server doing it, I forgot. We've kind of done both. Kotesh, client, right? So we kind of send an e-remote to the client. And so we won't send an e-remote because JBR is using e-remote, but then we'll send something like an e-remote to the client and that will basically go fetch the relevant data. Kotesh, yeah.
The question is, there are two discussions to incorporate the principles of DHT2 to the existing DHT, right? So what are your thoughts on what part of the DHT2 can the existing DHT2 can incorporate?
So the question is, there are some thoughts on incorporating some ideas from DHT2 into DHT. What are your thoughts? Okay, so let me give a crisp answer. There is a longish answer here. So A, and there's a good question. So I'll give another messaging here. So A, we are not, once DHT2 comes out of the door, we are not saying bye-bye DHT and saying, okay, let's all go to DHT2, this is the best and whatever it is, and life's good. There are enough number of volumes out there that are using DHT. The backend file system is non-compatible with between DHT and DHT2. It's just totally different. We are not going to provide a way to migrate. Simply put, that will just be a headache. If you want to do that. So DHT will coexist with DHT2 for some time, and if DHT2 proves that it is a good solution for the list of problems that we've been seeing, assuming that. And at that point, if DHT2 proves that it can really replace DHT for all workloads, we'll probably shift out and say DHT2 is the future. But that is not going to happen day zero. Why I started with this part of the answer is because, which basically means we need to work on DHT as well. I mean, we cannot just let go of DHT and say, hey, these problems exist, but you know what, when DHT2 comes, everything will fix that. That cannot happen. So from that perspective, it's good to improve on DHT, take ideas from wherever it is and do it. So that would be my short answer. So the long answer can be interesting. Any other questions?
Okay, we'll hold here. Cool.
Thank you.
Thank you.